Thanks, everyone. Thanks for letting me have a introduction about what we have done with MeerKAT. I'm going to talk about the H1 tensor mapping project we're dealing with. So yeah, I'm Yi-Chao Li. I'm currently a postdoc at the University of Western Cape, and previously was working with India in UKZN. Okay, H1. So basically, we are talking about this 21 centimeter line emitted by the neutral hydrogen with the spin fate between two stage. So the rest-free line width is 21 centimeter, and the redshift to us. So by observing this emission line, we can know the H1 intensity at different distance. So about H1 is a very common signal in astronomy. So it has been observed by many different telescopes and in a long time. So here's an example of the emission line of the galaxies observed by Arecibo in this Alpha survey project. So, and also recently with the large interferometry arrays, you can resolve this H1 within the galaxies, and you can see the distribution of the H1 within the galaxies and very clear. So basically, H1 is played a great role in astronomy for studying the galaxy evolutions or galaxy environment and group environment. Also, for cosmologists, it's very important because you can observe H1 in different stage of the universe, up to very early in the universe, and down to the late stage of universe, like redshifts of about 1 or 2. So at different stage, H1 is being showing up as different signals. Like at the early stage, you can observe H1 like an absorption line against the background, and in the later stage, because H1 is mostly involved in the galaxies, so it's going to be a good tracer for the galaxies. So basically, for cosmology, we can trace the galaxies by observing the H1 in the galaxies. There's a couple with like H1 galaxy survey is going on or is already done. Like we have mentioned this Alpha survey previously, and also there's others like Hyper survey, and also Uden VRA have doing some H1 galaxy survey, and also recently for ASCAP and MeerKAT, which is the pathfinder of the SKA, they're also doing H1 survey, galaxy surveys. However, if you do the H1 galaxy surveys, it's quite like time consuming. It takes a lot of time and need like a large interferometry to resolve these H1 galaxies. It is not suitable for the cosmology studies because you cannot have a large volume or higher galaxy densities. So in this case, there's another technique called H1 and tensor mapping, which is quite suitable for the H1 for the cosmology studies. So the idea for the H1 and tensor mapping is like instead of observing each of the galaxies in the universe, like galaxy survey, we observing a total flux density of a bunch of galaxies within small volumes. So in this case, you cannot really resolve each of the galaxies. You losing some information on the small scales, but you still have the large scale informations. For cosmology, we are more interested in the large scale scales because this is more linear involved in the history, so it's quite good for constrained cosmological models. So here's a plot showing how this scales being affected with the different telescope. Like if you use a MeerKAT L band, it's 1 degree resolution. You probably lose information beyond this area, but you still have a big future about BO on large scales. That's very promising for cosmology studies. And also, if you push to the MeerKAT UHF band, this is very low frequency, high redshift. You probably lose a lot of signals on here, but you still have a signature on the super large scales. So because you don't need higher resolution, the H1 tensor mapping can be carried out with a single dish, and you can have a very large observing volumes. So with these large volumes, you can like beat down the cosmological variance and have a good constraint on the cosmological parameters. Here is the example of the forecast. There's lots of forecast studies about this research. Here, just the example, let's compare in the intensity mapping and the galaxy survey. You can clearly see that the intensity mapping can have a large volumes compared to the galaxy survey with the similar time observation time, and also have a good constraint about the cosmological parameters like the sigma 8 compared to the galaxy survey. So and also H1 survey can provide multiple redshifts, which is also important for the cosmology studies compared to like photometric survey or continuum radio surveys. Also, H1 provides like a new tracer of these galaxies or of the dark matters, and combined with other tracers like galaxy survey in the optical band with different group of galaxies, you can apply the multi-tracer technique to even to further beat down the cosmological variance on large scales. You can have good constraints for the cosmological models. So basically, H1 intensity mapping can be used in different cosmological topics and have a good future for the cosmological studies. Also, H1 is not only the emission line can use for intensity mapping. There's other lines can be used as an intensity mapping tracer. But different line by observing different emission line, you can observe you actually exploring different stage of the universe and different scales. So there's this discussion in this paper, and people call this not only H1 intensity mapping, but call it line intensity mapping with different kind of lines. Okay, so this kind of a technique has been proved a long time ago. So the first observation with this emission line, with this H1 intensity mapping is done with this project. They using the Green Band telescope to do a H1 survey and cross with the Deep 2 galaxy survey. So they measure these correlation functions between these two surveys, and you can see there's a positive correlation between these two observations. That's showing that this technique is work for the cosmology studies. And later on, with more data being collected by the Green Band telescope, they kind of achieve this cross correlation power spectrum. So this is an image observed by the Green Band telescope before and after subtract the bright sources in the front. And this is a power spectrum they measured between the cross correlation power spectrum between the GBT intensity mapping and the VGZ galaxy survey. And later than that, there's a couple of detection is being reported mostly using the Green Band telescope and Parkes telescope. This is the two major large telescopes in the world. This is a recently reported result using the Green Band telescope and cross with different catalog within the same field, like the cross with the VGZ field, and as well as the ELG catalog and LRG catalog in the both EBOS surveys. So basically, this is a major detection about the cross correlation between H1 and galaxies. The autocorrelation of the H1 intensity mapping is still under detection. So that's the current stage of this H1 intensity mapping observations. So currently, besides this Green Band telescope and the Parkes, there's a couple other telescope has been used to do the H1 intensity mapping. Here's a kind of a review here. For example, the TNLI project is been built in China. It's already been observing for a couple of years, and there's a couple of papers come out. It's mostly for the technical adjustment. And also CHAM has been built and observing for a long time. There's a lot of alpha detected by CHAM, and also they're still working on the H1, and I think. And also in South Africa, especially in UKZN, there's a HyREX project. And also there's a single dish project called Bingo. This also doing H1 intensity mapping, but it is compared these three. This is only the single dish, but with multiple beams. Also, there's a FAST is been built and I've been testing for 1 or 2 years. So we also have some observation with the FAST. So at the end of this talk, I will talk about this with 2 slides. So the main focus of me is working on the MeerKAT here. So that's this involved in the MeerKLASS project, but we are most focused on the single dish mode. So all of this is targeted as a low redshift. I mean, low redshift means redshift around 1 or 2, compared to this project, which is target the UR stage, which is a high redshift. So basically, it's a paper now called HERA in South Africa, and also 21 CMA is in China. So and the low far MWA. Besides all this, there's another project. They are not looking at the H1 signal power spectrum. They are actually observing the global H1 signals like the ages and Prism. And also in China, there's a space mission called DSL. The Chinese name is Hongmeng. They also doing this like global H1 signal detection, but it is a space mission in the lunar orbit. So this is a different kind of observation style compared to what we have been done like this. So I will talk about this the MeerKAT H1 system mapping. So this project is involved in this one is called MeerKAT Large Area Synoptic Survey. So this is a kind of a combined survey project, including not only the cosmology studies but also galaxy or cluster studies. So the main purpose of this survey is trying to get like 4,000 degree square survey area at some very high sensitivity, and using both the L band and UHF band is a huge redshift range. So for cosmology, we most focus on this single dish intensity mapping, but for the rest of them is mainly using the interferometry mode to do the image and more details studies. So for cosmology, there's a couple of forecasts for the MeerKLASS to show that with the certain observations area and observation time, we can have a significant detection about auto power spectrum or cross power spectrum. And with this detection, we can make good constraint on this like omega H1, as well as other cosmological parameters. On the other hand, there's another sort of this project using the multi-tracer technique to give a constraint on the non-linear non-Gaussianity on the super large scales. So that's some other aim of this cosmological studies. So what's I actually working on this is the pilot survey, which is like a start of this MeerKLASS survey to test this technique and also our pipeline. So this pilot survey is we have been it's kind of already done with the first stage observation. So we totally have like a totally 170 square degree area, observation area, and collect about 10 hours for like 6 dishes observation time. So when we observe this field, we using a very stable observation mode, like fix the LT, the elevation of the telescope, to do the research scan. So what we use is error band is range from 850 megahertz to 170, 1,700 megahertz. but actually the useful bandwidth is not this high. This most part is contaminated by the I-Fi. The reason the area we select is overlap with the VGZ sub area. And also the background is also overlap with the Sloan catalog, which is the DR12 low-Z catalog and the CMS catalog. So basically, this is only a small area, but 170 square degree is mostly used for the testing system training the pipeline. And also still, we are trying to get some cross correlation with the background optical surveys. So for MeerKAT, we have something like it's good for the H1 tensor mapping. One is like they have 64 digits. It's very powerful. Like even with our pilot survey, this 10 hours observations, we already collect about 600 hours observation time. This is kind of a deepest H1 tensor mapping survey so far. And also MeerKAT's temperature is about 16 Kelvin. It's quite low and very stable, which is very good for H1 tensor mapping. In addition, it's like we have already measured the MeerKAT beam using this kind of a hydrographic technique. So this quite detailed beam, quite accurate beam model for the MeerKAT, and this model showing that the side lobe of the MeerKAT beam is lower than the sync function, especially at the far end, and there's a good agreement with they call it cosine beam model. So the blue one is actually from the measurement, and the purple one is the cosine beam model. And this model is being used in our analysis. So yeah, and the pipeline for the MeerKAT data, the pilot survey data is quite standard. It's basically include the like I-Fi's flagging, and we use null stout as the real-time calibrator, and also the point source, using a point source to recalibrate the null stout. So in Jing's paper, she also include this kind of Bayesian-based calibration processor to have a good constraint on this gain of this test scope. So far, we have a simple map-making processor, just grade the data into the map with a simple grading. So next step, we are trying to do some standard map-making processing, which is same as previous CMB did. There's a couple of different weighting methods. Basically, the most common used is this one, is using the noise inverse as a weight to make the map. There's a sense here is if you want to use this model, you need to know the noise model. So basically, a simple way to do this is just assume a very simple noise model is just only the white noise, and you just ignore the off diagonals. And more complicated, you can estimate the noise covariance matrix using the data. So this has been tested in the previous CMB, H1 tensor mapping. And now we are trying to do like we are trying to build a noise model and imply the noise model in the map making. So about the noise model, it's actually what I've been working on. We can model the noise in two parts. One is the white noise, which is uncorrelated in time and frequency. Another one we call this correlated noise, or it is called 1RF noise. So this noise is correlated across the time, and across the longer time, the correlation is more is more. So that's why this power is like inverse to the time interval. So this kind of noise has been explored in the previously Planck experiment, but in the previous explanation, it's only one frequency. But for each one, we have multiple frequencies. So we are trying to build the model not only across the time, but also across the frequency. We use the noise model, which introduced by Stuart Harper in his paper. So in this model, so the first time is just white noise, and the correlated noise is split into two parts. One is they call the temporal correlation, and then another one is spectral correlation. So both of this correlation is modeled as the power law spectrum, and the combination of these two can produce this kind of a wave noise signal. So this is one of the simulated wave noise. You can see this the noise is like some has some correlation across the time, so it's not like totally white. So in order to like test this model, we perform a little bit simulations. So like this, we found that there's a key parameter called knee frequency here, which is just describe the time scale that the white noise is equals to the 1 or f noise. But we found that this knee frequency is frequency resolution dependent. That is because the frequency correlation of the wave noise is different. If assume that the wave noise is not correlated across frequency, which is like it's behaved as same as the white noise, then when you reduce the frequency resolution, both the white noise and the correlated noise are both reduced, so the knee frequency keep the same. But if you assume that the one wave noise is fully correlated, like in this case, when you reduce the frequency resolution, the wave noise is keep constant, but the white noise is reduced by according to the frequency resolution. So that's in this case, the knee frequency is pushed to the high value. And in the between, if the wave noise not fully correlated, but not even non-correlated, is correlated at some scales, this shift of the knee frequency is quite dependent on the frequency correlations. So that's what we call the knee frequency is like nu dependent. So if you want to check how this wave noise affects the final power spectrum, the H1 power spectrum, you have to assume this kind of scanning patterns. Like this, if we assume the same scanning patterns as the pilot survey, like this, and then project this wave noise to the map and estimate the power spectrum compared to the pure H1 signal, we can see that even with a very weak wave noise, there's still some structures at large scales, which is overlap with the H1 signals. And also, if you vary the parameters in different way, you can see the effect is different. Like if you increase knee frequency, that means the system increase the frequency. That means the system is varying at short time scales. That makes the wave noise leak into the small scales. And also, if you increase the alpha, that means the wave noise it's correlated on long time scale, but very strong. That means that makes the power the wave noise power quite strong at large scales compared to this one. And also, this too is like you assume the power spectrum is fully correlated or fully uncorrelated across the frequency. That you can see the differences, different features here. So here we just assume you didn't do anything to the wave noise. You just leave it there, and it has a contamination to the final H1 power spectrum. So actually, we need to know how these parameters about this MeerKAT receiver system. So we perform additional observations to determine this parameter. What we do is like we doing additional observation by pointing the dishes to the source selection point. The reason we do that is like we try to keep the sky stable during this like 2.5 hours. So in this way, we can see the variance which mainly come from the system. So this is the waterfall plot, the raw waterfall plot. Not the raw waterfall plot. We actually do the bandpass normalization. You can see it's quite flat for the frequency, but there's a variation across time. And the white region here are just the I-phi, due to the I-phi, reflect the I-phi in this region. And then before you ask me the pulse pattern, we need to fill in the gaps here. We just using interpolations and add some white noise to this part. This is the gap filled time order data for two polarizations. And finally, we estimate the pulse spectrum. We call this the TOD or this time stream pulse spectrum, but it's 2D because we apply the Fourier transform both along the time axis and the frequency axis. So finally we got this kind of a pulse spectrum. So this is a tau. It's a Fourier transform of the frequency, which we can call this delay pulse spectrum. Delay. It's called a delay. And this is a Fourier transform of the time. So basically, the fluctuations here is mainly located in here, which means is correlated in the long time scales, and also correlated fully. It's like highly correlated in frequency. And this region is dominated by the white noise. Also. You can also project the cosmological scales to this plot, but you have to assume some scanning speed or scanning strategies. Here we just assume a very naive scanning strategy, like using the telescope to do a drift scan with 5 arc minutes per second scanning speed, and assume the observation frequency at 900 megahertz. So the scales is like this. So you can see this is the k equals to 0.5, this k equals to 0.1, and k equals to 0.005. So you can see the large scale is still contaminated by these variations here. But on small scale, this still has a lot of part is not affected by this kind of contaminations. But this contamination is not mainly from the system, because we actually point to the source selection point, but there's a variation here. Is basically from the sky, because the beam is not symmetric, and some other systematic issue can induce this kind of time variations. So we remove this time variation by using the PCA. We just do the singular value decomposition to the time order data, and remove the first several modes. You can see this just subtract the first SVD mode. This is 2 modes subtracted, and this is 5 modes subtracted. You can see after 2 or 5 modes subtraction, this is pretty like white noise. You can now see any structures or correlations. So this waterfall plot. But you can estimate the pulse spectrum using this data. As shown here, this is after 5 modes subtraction. Compared to this one, you can see the strong correlations has been removed. Like this part, and still remain some correlation at the corner, which is still the long time scales, and the correlation across frequency is leakage to the small scales. That means it's become less correlated across frequency. So and we can fit the model this pulse spectrum model to this data. that give a constraint to these parameters. So this is showing the best fit parameters for each of the telescope. So different color is just with different number of modes subtracted, and each point is one telescope. So this is two polarization. You can see that with the mode subtraction, the leaf frequency is being reduced to lower level. That means the correlation is being pushed into the even longer time. And also the beta value is pushed into higher value. That means the correlation across frequency is being reduced in this way. So basically, it seems that the PCA can remove some of the correlations, and we believe that this being removed correlation is mainly from the sky, and the remaining correlations we call it systematic wire noise. This kind of noise indicates that the leaf frequency is being reduced to like 0.03 hertz, and that means the one-off noise variation is well under the thermal noise over 100 seconds. So this is enough for the H1. So we can do the recalibration even out at these time scales. So within this time scale, we don't need to do anything. The system is kind of stable. And also this kind of thing can be used in the map making. If we have this noise model, we can apply to the map maker to do the linear solutions to solve this map. On the other hand, we also try to do some other things, like you can do they call the distributing method. Instead, we apply the weight to the map making. We can subtract these variations by fit this variation with some base functions. So this also been explored in the previously CMB analysis. But there's a problem for this one is if this fitting is not well fit to wave noise, it might cause some signal loss. So we need to figure out how much signal being killed in this distributing processor. So basically, it's kind of need to be competitive with some transfer functions. Yeah, this is something we're still working on. So after that, we actually in the same time we try to do the cross correlation power spectrum using current map. So as we know, we are overlapped with the UKZN catalog. So this is a catalog from the UKZN survey. And also, as we see, there's the background is SDS low Z catalog. This is showing the galaxy distribution of the low Z catalog. And this is the number of densities of these two catalogs. You can see UKZN has a little bit higher density compared to the both. I guess this is because some selection issue from the both survey. Currently, we mainly focus on this correlation, and this one is still has some issue. So the first thing we need to do is we need to remove the foreground. Currently, what I have been doing is using the PSA or you call it SVD, singular value decomposition, to remove the foreground. So this plot is just showing the eigenvalues decrease as a function of the number of mode. The different curve just showing with the different smoothing scales. The smoothing we smooth the map is try to reduce the beam effect, because the beam is like frequency dependent. We smooth the map to the same beam size, and then in this case we can reduce some mode mixing issue in the map. So you can see with the beam smooth, the eigenvalue decrease a little bit quicker than without this smoothing processor. But the mode looks quite similar between this different smoothing scales. This is just showing the first 10 modes here, and this showing the maps with different number of modes subtracted. This is the raw map just with the smoothing, and this is with 1, 5, and 10 mode subtraction. You can see after 10 mode subtraction, the scale is reduced a lot, and also this is kind of white noise in the middle, but still have some kind of contamination residuals at the edge, because this part is like poorly observed with the map. So besides this one, there's this PCA or SVD. There's other different foreground cleaning methods, like first ICA, or some we call this GMCA, or mixed GMCA with GMCA plus PCA. So people in the working group has been trying to do with different methods and try to clean this foreground with different methods. I think Weiming or India also have some other methods that's applied to this foreground, this map, and so this kind of different people have different job to do like this. So for me, because I have used the PCA, there's kind of always have some signal being killed in the foreground clean. So we use this transfer function to give a compensation to this signal loss. The idea is like we use the same mode which clean the real map to clean the simulation map, and estimate the power spectrum compared to the simulation without any cleaning method. So the ratio just tell you the signal has been removed during this cleaning method. So this plot is showing the transfer function as function of k parallel and k perpendicular. So we also include the beam in this transfer function, because then you can see this smooth the signal being removed on the small scales. This is mostly because the beam, and also the foreground removal is most affect the large scales in the bottom. So you can see with small number of modes remote, this part has been like highly remote. So this is have a very little signal remain in the map. Also, it affect the small scales a little bit, but not much. This is kind of a initial results we have right now. This is a cross power spectrum with different number of modes subtracted, and also with the transfer function applied. Basically, we have some positive constraint on this omega h1 and bh1 parameters, but there's some issue at small scales. We are not quite sure right now. We still try to figure this out. What's going on here? So basically, this is the current stage of our power spectrum estimation. Okay, in the last, I have few slides talking about the fast. So I have a chance to deal with a little bit of faster data, which is also H1 this mapping. But the full projects not only for this mapping is also dealing with a little bit galaxy survey, because the resolution, the beam size of the fast is 3 arcminute. At the low redshift, it can resolve some of the galaxies to do the galaxy survey. So right now we basically only use the error band receiver. It's cover the range from 1 gigahertz to 1.5 gigahertz. So we have 19 beams with sense temperature about 20 Kelvin. So far, the observation collect about 30 hours drift scan observations in night. So this is some data I'm looking at. Besides, there's another drift scan survey they call CRAFT, led by DD. This is a kind of full sky drift scan survey. There's a huge amount of data there, but yeah, there's some people looking at that one. When observing, when we do the drift scan, we rotated the beam array by some degree to let this cover this area. This is like a footprint of this current scanning part. So this is quite long along the RA direction, but very narrow on the declination direction. Is about 1 degree in the declination, but 6 degrees on the RA directions. Before any science output, we also test this YF noise for fast. So basically, we have doing the similar things as we did for the MeerKAT, but here we have 19 beams. For this test, we didn't rotate the beam array. So for each line of the array, they observing the same sky but at different time. So with this observations, they have observation about 8 hours drift scan overnight. So this is the kind of a 2D power spectrum estimate with the fast data. So similarly, you can see the sky is located at the corner of this 2D power spectrum. And also with different number of mode subtraction, this kind of contamination has been removed here. So something different compared to the MeerKAT, we have done like using the cross correlation between these 2 feet to remove the sky, because the sky is correlated between 2 feet, but YF noise is not. So with this cross correlation for sky subtraction, we can only subtract the sky and leave in the systematic YF noise in the system. So you can see the blue one is using the cross correlation, the red one is using the autocorrelation of each of the feet. So you can see if you use the autocorrelation, the knee frequency, sorry, is being blocked. This is the y-axis is the knee frequency. It's keep going down with number of more modes subtracted. But if you use the cross correlation, it can remain at some level. That's the level of this systematic YF noise in the system. So finally, we have give a constraint on this YF noise parameters is shown. Okay, so for some summaries, like we all believe that each one is powerful for cosmology studies. So right now we are trying to using the MeerKAT single dish mode to make it each one its mapping to real. So on this way, we using the kind of additional observation to give a constraint of the noise and make a noise model for the MeerKAT. And with this, we can use this noise model in the future map making or some other studies. So also we test this kind of SVD cleaning to the noise model. You can remove some of the foreground and get the systematic knee frequency, and the results showing that the system is quite stable over 100 seconds. For others, we are still working on the power spectrum or foreground cleaning. Yeah, that's some work is still going on. Yeah, thank you. That's all.
Okay, thanks, Yi-Chao. We can take some questions now. Inge, you can go ahead.
Yeah, I have a number of questions. First of all, I want to just to mention that this paper is also detection. Okay, but can okay, maybe I'll mention this later. So this first question is, in one of your plot that you show, there is a tau and as y-axis, which is in the unit of frequency inverse. does that means, but this is not interferometry, and this tau, what does this tau mean? This tau is not delay, right?
You can call it's just the Fourier transform of the time of the data along the frequency. So actually, it's kind of a delay.
But this is single dish. I mean, that doesn't have a physical meaning. It's just a Fourier transform, right? So. Hello?
It's actually yeah. This it's not this. It doesn't have the same physical meaning as the interferometry, but its physical meaning is similar to delay. But yeah, this you can just think it is the Fourier transform of frequency. Yeah.
Okay. And the other thing is, I can see there is a transfer function which you defined, and you went through that quite quick. Yes. What does that MS, and B mean? Can you just explain that again? Yeah.
Yes. So M is the map. S means the simulation map. So we use simulated H1 map. So the top is a cross correlation between two simulated H1 map. The power spectrum, which is correlation between two simulated H1 map. And in the bottom, we're using one of the simulation map, convolve with the beam, and clean with the foreground mode. So it's a foreground cleaning, and the beam convolution will remove some of these signals of the simulation map. And you do the cross correlation with the results with the raw simulation map, and get the power spectrum. So the ratio between these two power spectrum just to tell you how much signal is being removed in this foreground clean. Is that clear?
Oh, okay, and then from your plot that it shows, it look like the low K perpendicular seem to be mostly removed, right?
Yes.
Just from. But I feel that it should be the low K parallel, because that is the Fourier mode in the radial direction. So I'm expecting this plot to have the high value, the reddish stripe to be horizontal instead of vertical. Do you know what I mean? So, do you know what I mean? So, because you are doing like foreground cleaning, right? So, for foreground cleaning, to me, foreground cleaning to me should be remove most of the, if you can see my screen, like my Apple Pencil, to be the low K parallel, and that is the foreground mode. And if this is going to be removed, then this would more be kind of reddish at the low K parallel.
No. Sorry. What I plot is sorry. There's some confusion. This is the inverse of the transfer function. So yeah, that's the maximum is 1. So 1 means no remove. So the more remove, yeah.
Inverse.
Yeah.
Okay, inverse. Okay, that's okay. That's okay. Yeah.
Sorry, this is just some confusions.
Okay, and there is the other plot which should show the reconstructed power spectrum of the of the MeerKAT cross WeGoZ. Yes. And I understand this is still kind of unpublished. I guess this is preliminary results, right? So it's kind of unpublished results, right? And we got the same thing, but in the correlation, kind of a angular space, or actually physical space correlation, which sent to Wei Ming, Deji, and Dennis for do halo model comparison. But in that real space setup, that there isn't such a kind of excess of the signal. So I wonder, I mean, just from the real space comparison, I remember that we look at the data and theory that seem to be matched quite well. But here in power spectrum, in the Fourier space, look like the data is obviously much higher than the theory, or let's say on the constant bias model. So why these two doesn't match?
What do you mean in real space? You have a correlation function?
I think we are fitting the correlation function to the real space data. real space cause correlation. But then there isn't, I mean, the theory and data match pretty well. But here, look at in Fourier space, there is a large excess on some k around 0.2. No.
Did you apply the transfer function to the correlation function?
What do you mean a transfer function?
This signal compensation here, because this part is mainly come from this this part. So this kind of if you don't apply the transfer function, this part is kind of smooth with the beam. It should be very low. But after that, this is come out. So I'm not quite sure why this is come out. It's probably because the beam we are using is not quite accurate, or maybe it's too sharp compared to the real beam. That's why they push this signal up. But I'm still not sure. This was still investigated about this. But if your transfer function is not applied, this kind of transfer function, you cannot see the bump on the small scale. It should be removed.
Okay, let me explain. We just take the data from you or from Mario about the real space correlation function, and we don't process anything on Fourier space. We think that is the ending result of the real space correlation. So all we do is to kind of trying to fit the data with a theory with constant bias model, etc. I think we may have a offline discussion after this with Arodeji, Dennis, and Wei Ming, and then if you have a time, then we just to have a look of this in details. Yeah.
But I'm not sure. Are you sure this is a real space power spectrum? I'm not sure what do you mean real space power spectrum. I only give you this power spectrum, not in real space. It's in a Fourier space.
Okay. 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 Maybe I remember that. Maybe I didn't remember that clearly. So okay. So we can.
But also this plot is plotting the k-square multiply the pk. So this it has some amplify on the small scales. So that might be what you say is different.
Okay. And the other thing, I think that's all my questions. Just last one comments. Now, basically, I just want to show to Yi-Chao that this is my recent work with Dennis on the detection of 21 centimeter intensity mapping, but by direct stacking. I think you also know of this, right? There's this paper, and we had previously the direct stacking of filaments, and we found no detection. This is we stack on the halo itself. You can see on directly on the halo of 48,000 galaxies of 2DF, and we find the total detection of 12 to 13 sigma for 10 and 20 modes removal map, and those maps were processed by possibly you or other PAX members. So just to remind you that this is one of the very recent result of the PAX of the 21 centimeter detection from the PAX. Yeah.
Okay, that's great.
And thanks everyone for joining. Next week we have Shazri Mohammed from SAO giving a talk. So please try to tune in for that too.